Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Intermolecular forces. If we look at argon, it's a molecular gas, a monatomic molecule, atoms. However, it does form a solid at very low temperatures indeed. That means there must be intermolecular forces, forces between the atoms of argon, and heat energy needs to be supplied to break them to transform the solid into a gas. However, those intermolecular forces must, in the case of argon, be very weak. So, having established that there must be some forces of attraction between atoms' molecules that are not formal covalent or ionic bonds or metallic bonds, we come to discuss the nature of these intermolecular forces. Now, there are three types. If you have met this topic before, pause the video and write down what you recall of the three types of intermolecular force that you will meet at A level. So the first type would be induced dipole-dipole attractions, and they are known in OCR A specification as London forces. We could have a permanent dipole attraction, and then a special case of permanent dipole attraction, which we will call hydrogen bonding. So OCR A specification requires you to know the detail of these three types of intermolecular force. So how do London forces arise? Well, let's stick with our noble gas argon, and we have to take on board the changed ideas about electrons at A level. That is, that they are moving randomly within regions of space around the nucleus, not in regular orbits. In which case, it may be very possible for the electron density to suddenly and randomly favour the right-hand side of the atom as I have drawn it rather than the left. So we have an instantaneous dipole. So a delta plus where there are less electrons and a delta minus where there are more electrons. If a neighbouring atom of argon lines up to the original atom, then as we have delta minus here, it's going to drive the electrons in the neighbouring atom or repel the electron density in the neighbouring atoms, so that we now have a new induced dipole, delta plus and delta minus on the neighbouring atom. Of course, that will then happen in a sequence of events, so we have, as it were, a cascade of induced dipoles, and of course the oppositely charged dipoles, delta minus, delta plus, are going to attract. And that is the basis of London forces. Okay, so a typical problem involving intermolecular forces might be explain the trend in the boiling points of the halogens. So the halogens are written as X2. I hope you're familiar. Well, I'll make you familiar if you're not. So by that I mean any halogen, Cl2, Br2, I2. Okay, so we write the general formula as X2. So we've got chlorine, bromine, iodine. Okay, so what how would we explain the trend? Try to use the idea of London forces to explain the fact that chlorine has a lower boiling point than bromine than has iodine now. Okay, so continuing, what we need to realize is that the more electrons that are present in a molecule or an atom, then the greater the chance of random fluctuation, that initial fluctuation of electrons, which then induces the fluctuation in electron density in the neighbour. So the numbers of electrons present in iodine is much greater than in a bromine molecule than in a chlorine molecule. So this is a crucial key, because that means that the temporary dipoles that are created and induced by random electron fluctuations and the induced electron fluctuations, as described in London forces, okay, are greater. And that means if the temporary and induced dipoles are greater, then the forces of attraction between the molecules will be greater. That is, the London forces are greater. If the forces of attraction are greater, then more energy is needed to overcome them. So the term overcome them is a term that is accepted by OCR to mean breaking of them. So you put energy in to break a bond, for instance, you're able to refer to that as overcoming the bond, the forces of attraction of that bond, as it were. So let's consider permanent dipole attractions. These intermolecular forces occur in addition to the London forces that arise between molecules. If we compare the boiling point of ethanol to that of propane, we see the boiling point of ethanol is much higher. Yet, as they both have a relative formula mass of 44, the London forces that arise between each of the types of molecules is the same. So we'd anticipate, on the basis of London forces alone, we'd anticipate that the boiling points would be similar. If we look at the ethanol displayed diagram, we can see there's a polarized carbon-oxygen bond. If I introduce another ethanol molecule and then compare that to two propane molecules, I'd like you to pause the video and write out an explanation for the boiling point of ethanol being greater than that of propane. Resume the lesson when you are ready. So, the permanent dipoles that exist in ethanol result in there being attractions between the delta minus and delta plus elements of that dipole. So, we've got permanent dipole attractions plus London forces. Between the molecules of ethanol. However, between the molecules of propane, we have only London forces. So it follows that the intermolecular forces in total between ethanol molecules are greater than occur between propane molecules, hence more energy needed to break them, hence ethanol has a higher boiling point. Hydrogen bonding is the strongest form of intermolecular attraction or intermolecular force, and is a special case of permanent dipole attraction. Now, for hydrogen bonding to occur, there must be two circumstances. Firstly, we must have a hydrogen atom directly bonded to either nitrogen, oxygen, or fluorine. So we must have nitrogen directly bonded to hydrogen, oxygen directly bonded to hydrogen, or fluorine directly bonded to hydrogen. Those must be within the molecule. Now, of course, nitrogen, oxygen, and fluorine are the three most electronegative elements in the periodic table, and therefore that results in a polarization of the bond, or that electronegativity results in a polarization of the bond with hydrogen, and we have hydrogen being highly polarized. So hydrogen is delta plus, but significantly delta plus. The second circumstance is that there must be a lone pair of electrons on nitrogen, oxygen or fluorine. The lone pair of electrons are intimately involved in the hydrogen bond. So nitrogen has one lone pair, oxygen, by the way, has two lone pairs, and fluorine, oops, haven't quite got room, but I'm going to squeeze them in, three lone pairs. However, there's only a requirement for one lone pair for hydrogen bonding to occur. So let me model the hydrogen bonding between water molecules. So we'll take as our starting point H2O, which is V-shaped, if you recall. We'll put in the polarities, and we'll put in the lone pairs of electrons. I need now another water molecule. Again, taking care to get the V shape of the water molecule set out. Put in lone pairs for the oxygen again. Now the hydrogen bond will occur between a lone pair of electrons and a hydrogen delta plus of a neighbouring water molecule. Notice that bond angle between the hydrogen bond and the oxygen-hydrogen covalent bond is 180. So that detail is sometimes required in examination. So just to recap, we have a lone pair of electrons on an oxygen atom, which is delta minus, electrostatically attracted to a highly polarized hydrogen atom of a neighboring water molecule. The lone pair points at the hydrogen. If you look at that, the way I've orientated that, the lone pair points at the hydrogen atom. So that lone pair is constituting the bond. So we've got an attraction there, or a hydrogen bond between the oxygen lone pair and the hydrogen delta plus. And then the final detail, this arrangement around the hydrogen should be linear, the bond angle of 180. So using the idea of hydrogen bonding, dipole-dipole, permanent dipole attractions and London forces, can you explain why ethanol has a higher boiling point than ethanol? Pause the video, write out your explanation with as much detail as possible, come back and check against mine. So, ethanol has a lone pair on the oxygen atom, has a hydrogen bonded to the oxygen atom, and therefore if I draw out the molecule, you can see that we've got the special circumstances in which hydrogen bonding can occur. If I line up another ethanol molecule, we will see that the lone pair of electrons on the oxygen of my left hand ethanol are pointing directly at the hydrogen delta plus of the right hand ethanol, and therefore attractions can form between those two components. So here I have added in a dotted line to indicate the hydrogen bond. So here is our hydrogen bond, which is normally indicated by a dotted line between the lone pair of electrons on an oxygen, delta minus, and hydrogen delta plus of a neighbouring ethanol molecule. That blue dotted line on my diagram is the hydrogen bond. It is the strongest type of intermolecular force. Therefore, the energy needed to separate ethanol molecules is greater than the energy needed to separate ethanol molecules. If you remember, ethanol we did earlier has got permanent dipole permanent dipole and London forces, but the strongest type of intermolecular force is the hydrogen bond. So the intermolecular forces between ethanol molecules are stronger, and therefore it has the higher boiling point. More energy is needed to break them. So let's look at a problem straight off an A-level paper. Describe the intermolecular forces that arise between the molecules of ammonia in the liquid state. Well, I'd like you to consider that and write a detailed answer. Pause the video, come back when you are ready to check against mine. Okay, so the first thing to say, of course, is that as ammonia molecules have electrons, there will be London forces between the ammonia molecules, but we will also have hydrogen bonding. So let's look at the detail that you'd need to provide here. Well, we need to show that ammonia contains a polarized hydrogen-nitrogen bond and a lone pair of electrons on the nitrogen, and if it aligns itself with a near neighbor, that a hydrogen bond can occur between the lone pair of electrons on the nitrogen atom and the highly polarized hydrogen atom of a neighboring ammonia molecule. Probably worth saying that, as far as an exam mark scheme might be concerned, that the hydrogen bonding is the strongest type of intermolecular force. Let's look at the evidence for hydrogen bonding being the strongest type of intermolecular force, and that can clearly be seen if you plot the boiling points of the group 6 hydrides against their relative molecular mass. So pause the video, plot that data, and then try and explain the two trends that are seen. Come back when you're ready and check against my explanation. So my plot looks like this, and I'm going to use in my explanation the term van der Waals forces, which is a useful term because it just lumps together London and permanent dipole forces of attraction. So we can see that as tellurium is much bigger, so hydrogen tellurinide is got more electrons than hydrogen sulfide, we can see there's an increase in the boiling point, and that would relate to increased London forces as we go with an increased relative molecular mass. And that's the trend we would expect to see. However, we would expect to see on that basis water having a boiling point somewhere down here. But as we can see, water's boiling point is up at 100. Now the difference between the expected boiling point down here due to van der Waals forces and the actual boiling point up here is accounted for by the strength of the hydrogen bonding that exists between water molecules. So if water just had a normal permanent dipole and London forces situation, we would expect the boiling point to be down at the bottom here, below that of hydrogen sulfide, but in fact it's at the top here at 100, and that is accounted for by the fact that we have got hydrogen bonds present as well as London forces. So we've got a special type of permanent dipole that is much stronger than the permanent dipole that we see in the trend hydrogen sulfide to hydrogen tellurinide. If you If I gave you the data for group 7 and group 5 hydrides, you would see the same anomalously high boiling point for hydrogen fluoride and ammonia. But to save time and your patience, I'm not going to ask you to do that. The OCR A specification requires specific knowledge of the density of ice. Ice is less dense than water. Those of us who live in a cold climate know that as water turns from a liquid to a solid, it expands, and that can cause considerable problems. It also explains why a cube of ice floats in a cool drink of iced tea. However, we need to know the chemical basis of this. We assume that in the liquid state, water molecules are in a disorderly arrangement, represented here. So we've got the V shape for water molecules, of course. So V-shaped water molecules in a disorderly arrangement, representing the liquid. So the disorderly arrangement is thought to exist in a liquid. And in that disorderly arrangement, the water molecules can fit relatively close together. However, if we then look at the arrangement in the frozen solid, we assume, or we explain the expansion on the basis that there is an orderly hydrogen bonded structure created. So if I focus your attention on the central oxygen or central water molecule here, this central oxygen has covalent bond here and covalent bond here to form water, but forms also two hydrogen bonds here and here. So we have essentially around that central oxygen atom 4 hydrogens arranged tetrahedrally. Now that is like the diamond structure that you've met possibly in pre-A-level chemistry. And the average distance of the hydrogen and oxygen atoms is greater in the orderly hydrogen bonded structure, the diamond-like structure, than in the disorderly. And hence moving from liquid to solid. So if we go from liquid to solid, we go from disorderly to orderly diamond-like. There's an expansion in the volume of the material. So molecular lattices, substances like iodine, which you'll be aware of existing as diatomic molecules, I2, they form a vapor at very low temperatures. You may have done that in the lab, heated a little iodine in a fume cupboard and found you get your purple vapor. The question you have to answer at A level is, why is a crystalline solid so easy to vaporize? Would you think about that carefully and write down your thoughts now? Well, the answer lies, of course, in intermolecular forces. Although iodine I2 is covalent, nevertheless there are intermolecular forces between it, and I've just drawn a rough sketch of the sort of structure that you might expect for the iodine. So this is one face here of a cube, and we've got iodine in each corner and then iodine in the center of that face, and that would carry on with the other 3 faces that you can't see. So that's the type of molecular lattice that iodine would form. But of course the key point is that we have a regular arrangement of iodine molecules. They are only held in place by London forces. There are no chemical bonds between the iodine molecules, key word. However, there are random fluctuations of electrons within the molecule itself, producing instantaneous dipoles and inducing dipoles in neighbours, from which we get weak forces of attraction called London forces. As they are weak, they are easily broken or overcome, and therefore iodine place that into an evaporating dish and heat it under a very low heat from a Bunsen burner, will form the purple vapor that you saw. Now, one of the properties of molecular lattices that you'll be expected to explain is the solubility in water. Now, iodine is insoluble in water. Could you map out your ideas as to why iodine is insoluble in water? Try that now. Okay, so we need an explanation of the fact that iodine is insoluble in water. Iodine molecules are non-polar covalent molecules. So they are covalently bonded, but because the electronegativity of iodine on the left and on the right are identical, that is a non-polar bond. The interactions with water are very limited. They certainly cannot hydrogen bond with water, and therefore the intermolecular forces formed between iodine and water are very weak. So I think as an initial idea, although more detail will be needed in year 13, okay, when we look at ionic compounds in more detail and solubility in more detail, the simple notion that will account for the lack of solubility of iodine is that it is not able to hydrogen bond with water. Now, what about molecular lattices and electrical conductivity? I'm hoping that it's fairly obvious, but we'll see. Set out your ideas. Would iodine be expected to conduct electricity either as a solid or as a solution or as a melt? Set your ideas out now. Okay, so continuing, let's have a look at how we might argue the fact that iodine is a non-conductor. For conduction, you need mobile charge carriers, and those are either, in our world of chemistry, electrons or ions. Either electrons or ions are needed for the movement of charge, and those ions or electrons need to be mobile. Well, if we look at something like iodine, where is the free electron? There are none. Where are the ions? There are none. So iodine, molecular lattice, and all molecular lattices are non-conductors because of the absence of mobile ions or electrons, which act as charge carriers. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.